Meet Rory. He's not related to Tyrion Lannister, and he doesn't do kids' parties, or bachelorettes, or weddings. Okay, well, maybe speak to me afterwards, and we can negotiate a price. So I like to use the cloud to prove I'm not related to him. So this is AWS, remember, not Azure. This is AWS recognition. And you can see there it's a bit small, but 99% probability I'm not Peter Dinklage. And I know what you're thinking, yes, but he, in the show, has a beard. That's also not me. There's a unicorn in the picture, but he walked in the last second. So what about kids' parties? So I scanned this image, and nowhere did it mention kids' parties. Okay, it does say motorcycle and vehicle and wood. Motorcycle? Okay, so this is like Jerry showed you, hey? Sometimes you need to just train it. This is my son's birthday party, so it was the exception. So I've got a lot to show you today. We're going to go through natural language processing basics. We're going to demystify machine learning. When you walk out of here today, you should know the basics. I've got a drop the mic demo, which is actually sticky taped onto my face, so I can't really drop it. And also why I don't know sarcasm, and let's attempt to learn it. And then we're going to do a conclusion. So first, a background. I'm an organizer for the Johannesburg Amazon Web Services user group. We have 800 members, and we're hosted at BBD every third Monday of the month, and we also rotate sometimes to VAT-IT and ABSA. So for a very long time, I've been telling everyone that I could to use the cloud. Well, everyone with a valid credit card. I literally have had discussions with people about their credit cards. And I try to convince them all that they got machine learning. You get machine learning. There's nothing underneath your chair. You get machine learning. You get machine learning. Because what I told them was that they could use the AWS Machine Learning as a Service, AWS Comprehend. It allows you to scan the text. So in this example, it's BBD is now able to provide services through the Amazon CloudFront Global Content Delivery Network. This Amazon Consulting Partner status enables BBD to design, build, migrate, and manage an enterprise in the cloud. That's kind of us. So you can use it to analyze text for entities. So in this case, BBD, Amazon, and CloudFront come up on the top right-hand side. You see, Mark, I do know my left from my right. And you can also give the overall sentiment for the text. So in this case, there's 99% probability confidence that this is neutral sentiment. But I felt like Sad Affleck. Because all I had done was try and convince people they didn't need to know machine learning. So I set myself a challenge. I was going to show them all and bring balance to the universe by teaching an AI sarcasm. Yeah, only half of them would get it, but I'll do it myself. So let's start. First, let's define natural language processing. We have already seen how machine learning as a service handles the text, and we have in our example text from before. So NLP identifies entities like organization, date, location, and counts the number of times an entity is mentioned. Once done, it returns a confidence score on each entity. It extracts the key phrases, counts the number of times a phrase is repeated, and returns a confidence score for that also. NLP can also return the dominant language. So in this case, the dominant language of our text is Great British. We can also get the syntax for each word. So NLP identifies word boundaries and labels like nouns and adjectives within the text. So the name BBD is actually a proper noun. I remember from my private schooling that this is different from other nouns. And the focus of our talk. We can detect the sentiment of the text. So as we've seen from our machine learning as a service, the text is neutral. So how is sentiment actually calculated? We've seen how it magically appears with machine learning as a service. But I need to show how it's done manually and also via machine learning. So manually, we scan a sentence and we detect the weighting of certain words. We then tally the overall sentence weight and determine if the text is either positive, negative, or neutral. So in this example, I have my legs ache. Ache has a negative sentiment of -2. You are the coolest. Coolest has a positive sentiment of 3. I hate Paul but encourage him. So this has an overall sentiment of -2. You can also use booster words, which affect the sentiment. Extremely is worth an additional 2. Punctuation effects. Double exclamation mark, extra 3 points. Emoji, the sad face, -2. So once we have our rules, we can create something called a sentiment tree out of the text. In this example, we're using the Stanford NLP movie review database to scan a movie review. So it gets all these movie reviews from IMDb. And the important thing to note that it actually has humans checking on the reviews afterwards, because all of you go in there and you be salty and you say yes or no that this review is positive or negative. So this review, it's a brilliant, honest performance by Nicholson, but the film is an agonizing bore, except when the fantastic Kathy Bates turns up. I've actually watched this movie. It's a terrible movie. Terrible. It's a movie called About Schmidt. You know, there's one of those movies that just want to switch on the TV and you just let your mind just go numb. So the blue on the screen there actually indicates positive sentiment, and the red negative. So the overall sentiment is actually neutral as the positive balances out the negative. So the positive sentiment would be, it's a brilliant, honest performance. And the negative would be, but the film is an agonizing bore. Then again, it goes into positive when the fantastic Kathy Bates. So when I scanned using this, the other text that we did there, BBD as a CloudFront partner, the first part of it was actually negative sentiment. The other part was positive sentiment. That's why it was actually neutral. So you can actually go on that link down there, and you can look at all the movie reviews and play around with sentiment trees. So once we've looked at doing this manually, let's look at machine learning. And now when I say machine learning, I can look at the audience there, and some of you have like this. It's really, really not that difficult. Most of you already have been using it. So who here has a smartphone? Okay, because I don't, so please can we have a GoFundMe for me, please? You've already been using machine learning, because your predictive text actually tells you what you're going to type next. And that has been around for a very long time. You also are using machine learning with Google Autocomplete. So Google Autocomplete learns from both yours and other searches. This was actually the only clean example that I could find for Google Autocomplete. You all should be ashamed. So when I first started on machine learning, I thought I could create a personal AI slave. I tried to create a pass-the-butter robot with Alexa, but the results were not as impressive as I thought. So I didn't understand the machine learning process, and I may have created Skynet. The machine learning process is pretty simple. It's only 3 main steps. You generate example data, you train a model, you deploy the model. In techie talk, you get your labeled observations. You produce both a training set and a test set. You track the training set into machine learning, which will create a prediction model. You host this somewhere and input your test set. By inputting your test set, you can then go and see the stats and determine whether or not your model is suitable. If it's not, you can go and retrain it. So machine learning is great, but can we use this process for big data? Big data is basically the gap between data you can handle via conventional methods and data you can't. It was triggered by a price drop in the graphics processors, the GPUs, and innovation in machine learning training. To process big data, we need a subset of machine learning called deep learning. So deep learning is a subset of machine learning. Machine learning and natural language processing have some overlap. Machine learning is often used for natural language processing tasks. However, natural language processing has a strong linguistic component that requires an understanding of how we use language. In machine learning, the feature extraction is a separate process. So calculating the text language is actually a feature extraction. In deep learning, the feature extraction and the classification are both part of the learning process. Deep learning is modeled on the human brain. Neurons are the basic unit of a neural network. In nature, neurons have a number of dendrites and a cell nucleus and an axon. When the neuron activates, it accumulates all of its incoming inputs, and if it goes over a certain threshold, it fires a signal through the axon, sort of. The important thing about neurons is that they can learn. In an artificial neural network, we have several inputs, and for each input there's a weight, the weight of that specific connection. When the artificial neuron activates, it computes its state by adding all of the incoming inputs multiplied by its corresponding connection weight. After computing its state, the neuron passes it through to the activation function, which normalizes the results. That sounded very data science-y, hey? Very, very science-y. Let's show an example. So let's start with an example. The quick brown fox jumps over the lazy dog. First, we take the source text, and then we break it into training samples. The quick, the brown, quick the, quick brown, quick fox, and so forth and so on. Once we have all the training samples, we can pass it through our neural network, and it creates coordinates, vectors of coordinates. These vectors are called Markov chains. So in this example that I put there, I had a lot of chats with a lot of people, and I understand the Lions to be some sort of soccer team, and the Tri-Nations to be some festival they play at. Okay, maybe not. The vectors that we create are used as points to display the text in a matrix of numbers. So here we have the letter O. We create the coordinates, and we store it as a matrix of numbers. The matrix is actually stored in a 3D plane that gives approximate difference between similar words. We see this example that our machine learning has stored similar words close to each other. So king to queen, man to woman, country to capital. So once we have our document of text, we convert it to a vector. We take all of those vectors, we average them out, and then we input it into the first layer of a neural network, the hidden layers. There might be a few of these. Then we create document classes from the last layer of the hidden layers called the softmax. So how does this look like in an animation? So at the bottom there, we have our inputs, we have our hidden layers, and then we have our outputs. So notice how the output is fed back into the input to learn the results on a continuous basis. Just like your predictive text that you're using. As soon as you change it, it learns, it modifies. The clever guys at Harvard, which I was refused access to, have a nice tool to let us see the path the neurons take. So in this example, I have a question from a dad wanting to buy some material for his daughters. For $15, what can I get my daughters? So let's activate it. And you can actually see, as you actually select over each text, each individual neuron firing through the network. So as we select also different word groupings, so I select dollars what can, then the path would change depending on what we select. So the previous slide also had the URL. You can go onto there and do this yourself onto the Harvard site. Once the model has been generated, we have a model of the vectors and their proximity to similar words. So in this animation, I've used a graph created from all the words in Wikipedia, about 100 billion. I find the word million and navigate to its coordinates in the vector. Each vector has also connections to other vectors. In this case, we'll see how the word billion is 10 degrees away from million. So you can actually use this graphing tool to create your own vectors, and a lot of software engineers use it to explore different software packages. NuGet, NPM. I found that no one really likes Polymer because it was just clumped in a little ball left by itself. Don't tell Mark. Oh, he's gone. So let's do a little bit of demoing to actually show you how easy it is to get started with this. So I am using Java because I bear the weight of my ancestors' mistakes. And I've got my little project there called DeepBBD. You can actually go into github.com, roryp/DeepBBD. It was a spur of the moment thought. So I've set up my little project, and I'm using a library called Deep Learning 4J. We like putting 4J on everything. And it's an Eclipse project, because a lot of projects go there to die. And the first commercial grade open source distributed deep learning library written for Java and Scala. So what does it do? So we've got some raw sentences.txt here. No, he says no now. Oh, what does she do? Question mark, the money's there. And it's also not normalized. And it's just gobbledygook there. It's 3 megs of just text. What we're going to try to do is we're going to try to vectorize that and look for a single word inside it. So the first thing that we're going to do is we're just going to read in the text. So not wanting to tempt the demo gods, I have templated everything out. So we read the raw sentences.txt, and then we create a sentence iterator and a tokenizer factory from that. After that, you create weightings. So remember when we discussed the firing of your synapses through your neural network? You have to assign weightings to those individual neurons to allow them to fire if they reach a certain combined weighting. So in this example, I've just created an in-memory lookup table. I've set the vector length of 100. Remember, even though I've set over 100, it will consume about 300 megs of my little laptop's memory. Do not ask it to normalize. So one of the normalize functions on vector normalization is called AdaGrad. I just set it to false. And then I pass in the same cache there that we created previously. There. Okay. Once I've got my weighting set up, I want to actually create something called hyperparameters. Think of hyperparameters as going down to the south and asking people why they tune their cars. Because you can. Hyperparameters are meant to be able for you to manipulate your model to get a specific percentage of accuracy out. If anyone can tell you that deep learning and machine learning is 100% accurate, they're wrong. Most models are only about 80% accurate. And they become more accurate the more times you learn, but they reach a certain threshold before you can actually get to 100%. So we are now we've created our model, and we're going to do our first learning. Oh, no, we haven't done our model. Word, vec, model. So there we've got our model. And we create all of these hyperparameters to aid in our learning. The first one is that we want to create one instance of looping through the entire text. So that's called an epoch. We want to have 2 iterations here, because I found if I don't do 2 iterations, my CPU just says no, and then it doesn't learn enough. My layer size is the same as, if you remember, the vector length. I'm seeding it with a random number. And then I pass in my iterator and my token factory, my lookup table, and my cache that we defined before. So I've got my weightings, I've got my model, I've read in my text. And now we're going to do the first time we're going to learn. So all I do is I go, if you remember there, we've got our vector, our word to vec there, and we just go .fit. When I first found this word, I was like, surely you could have used another word. And then I realized that data scientists actually just wandered into RT, used us, and then wandered out occasionally. So we're looking in that vector for the closest 10 words to million. We already saw in that universe that I created with 100 billion words that there were other words close to it. So we're going to try and create the first, output of the first 10 words. Once we have created that, we're going to save our results back into the model. We've learned something. We're going to save our results back into the model. So we get our results there, and then we actually save it back into the model. So there, vector. And then we learn again for a second time, and hopefully, depending on my antivirus, we'll see if we can actually change the results with our second learning. So I'm going to run this now. So it's telling me that I have 8-core CPU, 3.5 gigs, and now it's starting the vocabulary building. It's looping through all of the text, building up that cache. Once it gets the cache, it's going to assign our weighting, our default weighting, and then our model, and it's going to start the learning process. So I discussed with Jerry and Mark whether I should do a dance for you while this is happening, though, and they said no, but I'm going to just... No, I don't have anything offhand. Oh, how many software engineers does it take to change a light bulb? Oh, just okay. It's a tough crowd. So let's look at exactly what we did here. So we can see here we have started our epoch. We vectorized 652,000 words. And the first time we trained was 4 seconds. Closest word to 1 million on first run was several, 5, 4, few, 0.23 a go percent times in group. The second time actually looks exactly the same. Yeah, because I trained it back there. So sometimes it works, sometimes it doesn't work. I've learned to live with that, hey. Where's group? Yeah, group is at the end because I kicked it out with million. So we could sit here for a while, but the learning process eventually, it's very slight. And I realized that to really show you a good learning process, I had to use the cloud, not my actual individual laptop. And then you can have those monster Cray 1 computers that I mentioned previously. So what we're going to do here, where's that? Is I'm going to open up a Python Jupyter copybook. I've previously trained this on a AWS SageMaker instance. It cost me about £6. And we're going to now import data from the NLP Stanford index. You remember those movie reviews? Well, I have them all here. So I have the word and then the sentiment linked to it. So new, positive sentiment, splash, positive sentiment, and all the way back to Arnold Schwarzenegger. Universally disliked, it seems like that. So we have all of the different text phrases here. And remember, this is our training set, and then we have our test set. So we have our test set, and we have our little movie review here. Arnold's jump from the little screen to the big will leave frowns on more than a few faces. So that's our test set. We know that a human being actually went and said that is negative sentiment. So we can build a model that can try and mimic and determine sentiment for us. So we're using AWS SageMaker, which is a nice way to say that it's their machine learning system. And we're using MXNet and Gluon. Fancy, fancy words for saying it's an Apache library with, some other nice features. So this is a Jupyter copybook, and the interesting thing about Jupyter copybooks is that you execute the copybook from the same place as you actually see the code. So when I execute it here, I downloaded, and you can see there the data. It shows you the execution. So we have our imports, and then I get my training data and my test data, and I copy it onto the SageMaker instance. I then implement a training function, and the training function is actually based on an algorithm called Bag of Tricks for Efficient Text Classification, as implemented by Facebook's Fast Text for text classification. More data science. So if you want the actual sentiment.py, Python, where is that? Sentiment.py, and it's a lot of nice little NumPy arrays. And Gluon allows you, with the syntax, to actually go and determine your neural network using a declarative method. So we get the data, we upload it, we implement the training function, and then we run the script on SageMaker. So you see here, I've got my hyperparameters. So as we defined before, I'm specifying that I want to learn on an M1C4 2 times large, which has about 8 CPUs and no GPUs. I could have actually specified 128 CPU, 16 GPU monster. That is about $10 a minute. So I actually then did m.fit. We learned the actual model. And once you learn, then you actually go and deploy it to a instance. In this case here, I've deployed it to a little bit of a smaller instance, which I've been running ever since last night. Please let's let this demo finish so I can stop it. But it doesn't really cost that much. To train it costs about $6, and to run it over the course of 2 weeks has cost me about 100 Rand. So when you deploy it onto an SageMaker instance, it creates a REST endpoint that you can actually go and infer on it using a JSON array, which I have with Postman. So what I've done is I've trained 25,000 movie reviews, a lot of Arnold Schwarzeneggers, and now I have the ability to detect sentiment from certain words. So I love you, if we send that to I love you. What about I hate you? I hate you, 0 sentiment, because we know that hate in that all those movie reviews would eventually be linked to a negative sentiment. What about I love to hate you? What do you think it'll be? Positive, because the positive sentiment outweighs the negative. Okay, so this is basic grammar, but we're not here for basic stuff here. We're here for some sarcasm. So let me load in some sarcastic statements into it and see how it handles. Well, at least your mom thinks you're pretty. Life's good, you should get one. You look good when your eyes are closed, but you look best when my eyes are closed. Always remember that you're unique, just like everyone else. So what do you think we're going to do? None of these are actually positive statements. We'll push them through there. The first 2, it picked up that it was negative. The last 2, it actually picked it up it was positive. Because think about it. You could actually infer that the person was being positive. Why? Because it doesn't actually understand the sarcasm in the text. Let's discuss sarcasm. Let's first discuss what it isn't. It isn't irony. It's a part of irony. It's a specific type of irony. In this picture, we have a dilapidated house and a sign advertising home repairs. That's ironic. Now we have a stop sign where someone has spray painted the words defacing stop signs on it. Stop defacing stop signs. So we get a grasp on irony. It's using language that normally signifies the opposite. So what is sarcasm then? Let's use another sign. So the bottom sign says, go ahead, pull your huge SUV in at the last moment, everyone is okay with it. It's being sarcastic. Sarcasm comes from the Greek definition sarkasmos, to tear flesh with teeth, or the Sanskrit, a twisted utterance. It's different from irony. It relies mainly on intention. So sarcasm is a negative form of rhetoric in which neutral or pleasant-sounding words are used to make harsh criticism. We use it often, mainly on Twitter. So we use sarcasm on the internet to gently show people the correct path of righteousness. Why? Good question. So why do people hashtag sarcasm? They do that because not even human beings understand sarcasm. So in this here, American Air, you're doing great. Who could predict heavy travel between Thanksgiving and New Year's Eve and bad cold weather in December? Crazy. Kirsten, we love the kind words. Thanks so much. Wow. Just wow. I guess I should have hashtag sarcasm. Have you ever tried being sarcastic with a child? They look at you like, what the hell? Or most of your colleagues, actually. I think that they could also... So this was such a difficult thing. that the Secret Service put out in 2014 an RFP called the Social Media Analytics Subscription. And I went through it. One of the core deliverables is that they wanted people to detect sarcasm. It's still open if you want to actually go and reply to the RFP. Because threats made on the internet are sometimes sarcastic. And these guys really wanted to know, and still want to know, if the person is being sincere. So let's not try to test it, please. Lengthy jail sentence, okay? But it's clear that sarcasm is difficult to detect. But why? The reason is that the sentiment of a sarcastic remark can't just have a sentiment of a positive or a negative. We saw that there with a 0 or 1. It couldn't really determine whether it was sarcastic, and we didn't know whether it was being sarcastic. Social engagement follows a complex emotional spectrum. Interesting, this emotional spectrum wheel shows boredom as leading to disgust and loathing. Scientists have shown that boredom is an evolutionary reaction to your body feeling distressed it may be poisoned. So if you are bored, please, in my talk, please can you find the nearest paramedic, and he will prescribe a series of Netflix to help you out. Have you ever wondered why children will do anything to not be bored? So we have an emotional spectrum. What are we going to do with it? Introducing Deepmoji by those boys at MIT, the world's most advanced artificial emotional intelligence. So it's trained on 55 billion tweets, on your tweets. And how do they train it? Every time you tweet, you've put a emoji at the end of it. Happy face, sad face, not impressed face. And that emoji is you actually marking it as a sentiment. So they took 55 billion, they sanitized it to 15 billion, and they categorized it into 63 different separate emojis. Each emoji is linked to similar ones. The ones we care about the most are the not impressed face, the deadpan face, and the angry faces. Now we chuck the text through a neural network, and they came out with an emotional sentiment for the text flow. What do you mean by text flow? Because sarcasm actually follows a flow, the emotional flow, and you need multiple different types of emojis to show you that. Happy Affleck. So the first thing that I did, because we all love ESCOM, hey, I want to detect if it could actually detect some sarcasm at ESCOM. So I chucked in this text there. The electricity is off again, oh joy. And now you can actually see it came back with the emotional sentiment flow, showing that the words oh joy wasn't actually positive. What about other examples? I love mom's cooking. Smiley face, heart, something else, blush, heart. I love how you never reply back. Unimpressed face, deadpan, angry face, no emotion, broken heart. I love cruising with my homies. I love messing with your mind. I love you and now you're gone. Okay, so Tony says I can swear. This is shit, which is negative sentiment. This is this shit by my favorite poet, Snoop Dogg, who actually pronounces this as the shizzle, which is actually positive. Because a lot of sarcasm is based on slang. So when they read in those 55 billion tweets, they also read in the slang. Because you cannot detect sarcasm if you don't understand popular culture. You might be poisoned, hey, Taryn. You can chat to me later. So you can try it out also. So right now, you can take your phone and go to deepmoji.mit.edu. We still have, actually, I'm a little bit over time. But you can open up there. Now, every time you get a sarcastic email and you want to detect whether the person is being sarcastic, go into that link there, and then it will tell you the emotional emoji flow of your text. So you remember this? You got this. We have arrived at a golden age of cloud services. Per millisecond serverless architecture, local data centers around the corner, hybrid cloud architectures, 64 CPU, 16 GPU monster servers, nearly 800,000 times faster than the first Cray supercomputer. We are being disrupted, but that doesn't mean we can't be the disruptors. I challenge you, as part of your digital disruption strategy, embrace AI and deep learning. And maybe like me, start scanning your emails and get your pass the butter robot to help you detect sarcasm. Thank you.